Today I'm going to talk about LeetCode question number 155, min stack. So design a stack that supports push, pop, top, and retrieving the minimum element in constant time. So implement the min stack class, where this initializes the stack object. This function pushes the element val onto the stack. Pop moves the element from the top of the stack. Top gets the top element of the stack. And get min retrieves the minimum element of the stack. And each function must be over one time complexity, so constant time. Okay, so all these are pretty standard. The difficulty here is getting the min in constant time. So for example, looking at this example here, and here's our stack. So we initialize it, then we push -2, and push 0, push -3, okay? And then to get min, we can't simply traverse the stack. That'd be O of n time, where n is the length of the stack. We need to get it in constant time, okay? So in this example, get min, we return -3. And then after that, we pop, so we move this. And then top, we just return the topmost element, 0. And then get min again, and the minimum this time after pop in -3 is -2. So how can we keep track of this minimum element? Well, initially, somebody's initial thought might be to keep a variable in the stack class called, I don't know, min or something. And this will keep track of the minimum thus far. So, for example, if we start all over again here, the minimum so far when we push -2 is -2, and min is equal to -2. When we push 0, our minimum is still -2, then push -3, and this changes to -3. Okay? But the problem is with using a single variable is, what if we pop elements from the stack? Then what becomes a new variable? For example, if we pop -3, for 0, what is the new variable now? And how can we find that out without traversing through a stack? So this single variable approach won't work. But what if we think about this? So for every element that we push in this stack here, at that moment in time, there will be a minimum element. Okay? So what do I mean by this? When I push -2, at this moment of time, when -2 is the only element, the min so far is -2. And then what about when we push 0? At this moment, when 0 is pushed, -2 is still the min. And what about -3? Well, when -3 is pushed onto the stack, at this moment in time, -3 is the min. Okay? So when we do the get min function here, we get the latest minimum, which is at the top of this stack here, the latest element and the latest minimum. So what we return is -3. And then when we pop, we remove this. Okay? And then when we call the get min function again, we know what the minimum will be now, because now when 0 is here, the moment when the 0 was pushed, at that moment in time, -2 was the min. Okay? And it's still true, -2 is now the min. Okay? So this sounds a lot like initializing another stack, and this will be the min stack. Okay, so where -2, -2, and if we still have -3, the min would be -3 here. Okay, so this is how we'll go about it. Another way of doing this without keeping another stack is to create nodes. So we could define another class, like def node, and then, this should be class node. and then we create the constructor. We do it in Python, and what this constructor takes is val and min. Okay, so instead of just individual integers being stored in the stack, what we can do is store node objects, where similarly we store not only the value, like -2 here, but also the min, which is -2. That's another way of going in. I'm going to go with the two-stack approach for now. Okay, now what I'm going to do here is self dot stack, initialize our regular stack and our min stack. And remember, there'll be one-to-one mapping of stack to min stack, so whatever's at position 0 of stack, there will be an associated minimum value at position 0 of this stack, and this represents the minimum value at that for that node for that value at that moment in time. Okay, so for push, what we want to do is simply self.stack dot append val. And what about our min stack? What do we append to min stack? So we're going to simply compare whatever the latest minimum is and this current val, and whatever is smaller, we append that to the min stack. Okay. First, I want to check if len self dot min stack is equal to 0, and that means it's empty. Then we probably pushed our first thing into the stack. Then what we're going to do is self.min stack.append the val. Okay, that's no. Else, if val less than, what I'm going to do is min is equal to stack guy or else we're gonna, here's our latest minimum. If val is less than latest min, what we're gonna do is push val onto the min stack. Else we're gonna append the latest run-in minimum into our min stack. Okay. And for pop, that should be simple and it returns void, so we're going to simply pop from these two stacks. Stack dot pop, that should be syntax. Self dot min stack dot pop. Okay, simple enough. And top, what we want to do is get the top element of the stack. So we're simply going to return the very latest element on our stack here. Dot stack and get min. Similarly, we're gonna get the latest minimum value from our min stack. Okay, so most of the logic is in this push here, and doing most of that logic there ensures we have O1 runtime for the rest of these functions. And this is O1 too. There's more. It's just there's more logic. I'll try compiling. Oh, oops. Latest min. Okay. Try compiling again. square brackets. And similar here, send that copy paste. Okay, I think that looks good. Okay, great. I'll use this example here. And I'll submit. Okay, great. Thanks for watching.